Hi everyone, and welcome to more examples of integration by parts. I kept the formula up on this side of the screen just so you could see it, but we're going to really be focusing on these example questions. So the first example question, they gave us this, t squared e to the t dt. So I'm going to use t squared as u, because that one will definitely get simpler as I do my derivatives. Then dv is going to be e to the t dt. Now I'll do my derivative. Du equals 2t dt. And I'll do my integral here. So v equals e to the t. Now I'll follow the formula. So t squared times e to the t. And then I multiply the two bottom values. So minus the integral. Now this 2 I can pull out to the front because it's a constant. It's just a plain number. The other things need to be multiplied inside the integral. So it's t e to the t dt. Now I can't really do this integral because it's still a product. So I'm going to use my rule again. And you can use the rule as many times as you need to. So you can just keep using it until you can simplify out whatever expression you have and it becomes just a single function in there. So if you're going to be doing that though, what you want to do is you want to be very careful because you're going to have a bunch of numbers multiplied in. So watch out for the distributive property going on there. So I'm going to make t my new u, and e to the t dt is going to be dv. Okay, the derivative of u is going to be 1 dt, or just dt. And the integral of this is just v equals e to the t. Now I'll multiply the u and the v, and I can't forget to have this part here. So t squared e to the t minus 2, and I like to put brackets there, t e to the t, and then I multiply these two bottom parts, minus the integral of e to the t dt. Okay, this integral is just e to the t, and I have to distribute in my negative 2. So I have t squared e to the t minus 2t e to the t. Negative 2 times negative 1 is positive 2, and this integral is just e to the t, and plus c at the end. So that's that one. Okay, we're going to go on to this one next. Let me get that closer. Okay, so I'm going to pick this as my u. U equals x plus 1, and this is going to be my dv. Now, I picked this particular example for a very good reason. It's not actually an example from your book, but it's because right here, when I do my integral, I have to use substitution because this has a 2x in it right there. So I have to use substitution on that. The derivative of this is easy. This is just du equals 1 dx. But this integral, I have to use u substitution, so u is 2x. And a lot of times I use a different variable for that because having a u here and a u there is just confusing. So you can use a different variable if you want. Call it w if you want. The derivative of this is 2 dx, but there is no 2 in my integral, so I have to divide by 2. And now I can do my integral. So this becomes 1/2 the integral of cosine of u du. The integral of cosine is sine, so sine, and the u value was 2x, and I can't forget the 1/2 at the beginning. So this is the actual integral there. Okay, now I can apply my formula. U times v, so it's x plus 1 times 1/2, so I'm just going to put this over 2, sine 2x, minus the integral of the two bottom things multiplied together. Now there's a 1/2 here, so I'm going to put it in front, and it becomes sine 2x dx. Now to do this integral, again, I have to use u substitution. So I'm going to let u equal 2x. So du equals 2 dx. But again, there's no 2 in here. So I'm going to divide by this 2. And now I can substitute. So I end up with doing 1/2 times the integral of sine u du. Okay, now this integral is cosine, negative cosine. So negative 1/2 cosine, and the u has to be replaced again with the 2x. So that's the value for my integral. I can't forget that there was a 1/2 in front of that integral, and I should copy the rest of this down. So minus, and then you had the x plus 1 over 2 sine 2x. Moving down. Okay, I just have to simplify this part right here. So it becomes x plus 1 over 2 sine 2x. And then negative 1/2 times negative 1/2 is positive 1/4 cosine 2x. And don't forget the plus c at the end. So that was a really complicated one, but I picked it because it was complicated, so you could see a complicated example. Let's go on to an easier one. You'll notice that all of the other questions I've done so far as examples were indefinite integrals. This is a definite integral. And the only difference is that when you do a definite integral, you're going to evaluate each part as at these values. So this part here is going to be evaluated from 0 to 1. This is going to be evaluated from 0 to 1. It's the only difference between doing an indefinite integral and a definite integral. Okay, so in this one, I notice that I have two functions, the trig function and the dx. Okay, so it doesn't really give me much option. This has to be dv. Okay, which means that this has to be u. Okay, now we didn't really talk about inverse trig functions, but that's why I mentioned that table at the back of your book earlier. So using the table, you find that the derivative of inverse tangent is 1 over 1 plus x squared dx. And I just got that from the table in the back of your book. Over here, when I do the integral, I find out that v equals x. Okay, now let's apply the formula. U times v. So x tangent inverse x evaluated 0 to 1 minus the integral of these two bottom things multiplied together. That's x over 1 plus x squared. Because I did x times the fraction, this is x over 1. 1 times x, this times this, dx. Okay, now I'm almost where I need to be. Don't forget the 0 and 1. But I notice that this needs u substitution now, and it's perfect for that, because if I do the derivative of this denominator, then I get du equals 2x dx. Okay, so almost perfect substitution. I have the x and the dx right here. Okay, but the 2 is in the way, so I have to divide by 2 on both sides, and I'm allowed to do that because that's a constant. So now I can do substitution there. So this integral becomes the integral, I'm going to do it over here, of 1 over u du with a 1/2 in front. Now I did replace that u in there, so it's up to you if you want to later go back to terms of x and put this in for a u, or if you want to translate these into u's, and that's what I like to do. So I put 0 in for x squared, and I get 1 plus 0 squared, which is 1. I put 1 in for x squared, and I get 1 plus 1 squared, which is 2. Okay, and now I can just do this integral. The integral of 1 over u is just the natural log of u. And if you don't remember that one, that's a new one for us. Again, check that table in the back of your book. So this becomes, I can't forget this part, x tangent inverse x evaluated 0 to 1 minus, and then 1/2 the natural log of u evaluated 1 to 2. Okay, and now I'll just evaluate those. Now, tangent inverse, you might not remember where those come from, But tangent inverse of 1, when you put that in, I like to do that from the unit circle. At the unit circle, this becomes a pi over 4 because that's where the tangent is actually equal to 1. So this is 1 times pi over 4. Here, this multiplies to 0, so I don't even have to worry about what the inverse tangent of 0 is. Okay? Now, for this part here, it's minus 1/2 times the natural log of 2 minus the natural log of 1. Now, if you remember your laws of logarithms, this means the natural log of 2 divided by 1. And 2 divided by 1 is just 2. So the very simplified version of this is pi over 4 minus 1/2 the natural log of 2 plus c. And that's the final answer there. Okay, that's it for this video. Let me know if you have any questions or if you want to do a virtual meet.